Mastering artificial neural networks. Optimal CNN architecture demands careful balancing of kernels, filters, and pooling to conquer image classification chaos. When designing a convolutional neural network, CNN, architecture for image classification, what are the key considerations and essential components that one should prioritize to ensure optimal performance and accuracy in the model's ability to correctly identify and distinguish between different image classes? When designing a convolutional neural network, CNN, architecture for image classification, there are several key considerations and essential components that should be prioritized to ensure optimal performance and accuracy in the model's ability to correctly identify and distinguish between different image classes. First and foremost, the choice of network architecture is critical. The architecture should be deep enough to extract complex features from the input images but not so deep that it becomes prone to overfitting. A common practice is to use a combination of convolutional and pooling layers to extract features, followed by fully connected layers to classify the images. The number of convolutional and pooling layers, as well as the number of fully connected layers, should be carefully chosen based on the complexity of the classification task. Another essential component is the choice of activation functions. ReLU, rectified linear unit, is a popular choice for hidden layers as it is nonlinear and can help to introduce nonlinearity into the model. However, other activation functions such as leaky ReLU, sigmoid, and 10H can also be used depending on the specific requirements of the classification task. Regularization techniques are also crucial to prevent overfitting. Dropout, L1, and XYZ regularization can be used to prevent the model from memorizing the training data. Dropout, in particular, is widely used in CNNs as it randomly drops out neurons during training, which can help to reduce overfitting. Batch normalization is another essential component that can significantly improve the performance of the CNN. It normalizes the input data for each layer, which can help to reduce the internal covariate shift and improve the stability of the model. The choice of optimizer is also critical. Stochastic gradient descent, SGD, with momentum is a popular choice for CNNs as it can help to escape local minima and converge faster. However, other optimizers such as ATOM, RMSPROP, and ADAGRAD can also be used depending on the specific requirements of the classification task. The learning rate is also an important hyperparameter that needs to be carefully chosen. A learning rate that is too high can cause the model to converge slowly or oscillate, while a learning rate that is too low can cause the model to converge too slowly. The number of epochs and batch size also need to be carefully chosen. The number of epochs should be large enough to allow the model to converge, but not so large that it becomes prone to overfitting. The batch size should be large enough to provide a good estimate of the gradient, but not so large that it becomes computationally expensive. Data augmentation is another essential component that can significantly improve the performance of the CNN. It involves artificially enlarging the size of the training dataset by applying random transformations to the input images. This can help to reduce overfitting and improve the robustness of the model. Feature extraction is another key consideration. The CNN should be designed to extract features that are relevant for the classification task. This can involve using convolutional layers with different kernel sizes, strides, and padding schemes to extract features at different scales and resolutions. Another essential component is the choice of pooling layers. Max pooling and average pooling are two popular choices, but other pooling techniques such as stochastic pooling and spatial pyramid pooling can also be used depending on the specific requirements of the classification task. Transfer learning is also a key consideration. Pre-trained models can be used as a starting point for the CNN, which can help to improve the performance of the model and reduce the training time. Finally, the choice of evaluation metrics is critical. Accuracy, precision, recall, and F1 are popular evaluation metrics for image classification tasks. The evaluation metrics should be carefully chosen based on the specific requirements of the classification task. In summary, the key considerations and essential components for designing a CNN architecture for image classification include the choice of network architecture, activation functions, regularization techniques, batch normalization, optimizer, learning rate, number of epochs and batch size, data augmentation, feature extraction, pooling layers, transfer learning, and evaluation metrics. By carefully choosing these components, it is possible to design a CNN that can accurately identify and distinguish between different image classes.